Have you ever dreamed of walking through walls? In the everyday world, it sounds like pure science fiction. But in the quantum world, particles do this every day. Welcome to the strange and amazing phenomenon of quantum tunneling, where particles break the rules and slip through barriers that should be impossible to cross. Picture a ball thrown at a solid wall. Classically, if the ball doesn't have enough energy to break the wall, it bounces back or falls flat. It will never end up on the other side. Now imagine a tiny particle like an electron. It approaches an energy barrier, our wall in the quantum realm. It doesn't seem to have enough energy to get over that wall, yet, poof, there's a small but real chance it appears on the other side as if the wall wasn't even there. That is quantum tunneling. A particle tunneling through a barrier instead of going over it. How is this possible? The secret lies in the wave-like nature of quantum particles. In quantum physics, particles are also waves of probability. This means an electron or proton isn't just a tiny dot following a single path, but a fuzzy wave spread out in space. A wave that tells us the chances of finding the particle in different places. And here's the key. These waves don't abruptly stop when they hit a barrier. They fade away or taper off inside and beyond the barrier. If the barrier is thin enough, the wave doesn't drop all the way to zero. It leaks through to the other side. In other words, there is a tiny but non-zero chance the particle's wave sneaks past the wall. Once in a while, the particle will turn up beyond the barrier, as if it tunneled straight through solid matter. We can express this idea in a simple word equation instead of a math formula. It's like a rule of thumb for tunneling. Tunneling probability increases when the wall is thinner and the energy gap is smaller. In plainer terms, a particle is more likely to tunnel through if the barrier it faces is less thick, and if the particle nearly has enough energy to climb it normally. Make the barrier thicker or taller, meaning the particle's energy is much lower than the barrier, and the tunneling chance drops dramatically. Think of it as the odds shrinking exponentially as the wall gets thicker, but make the wall very thin or lower the height of the hurdle, and the odds start to grow. Let's break that down with a quick analogy. Imagine our particle as a very small ghost and the barrier as a wall. A very thick wall is hard for the ghost to get through. The ghost might not make it to the other side. A thinner wall, easier. The ghost has a better chance of slipping through. And if the wall is just a flimsy screen door, the ghost glides through with ease. Similarly, if the particle's energy is just shy of what's needed to hop the wall, it's almost pushing through. So the gap is small and tunneling is quite likely. But if the particle's energy is much too low, a huge gap, tunneling is extremely unlikely. Our word equation sums it up. Thin barrier plus small energy gap equals higher tunneling chance. Now, you might be thinking, this sounds like a crazy theoretical idea. Does it really happen in the real world? Absolutely yes. Quantum tunneling isn't just a quirk of theory. It's happening all around us and is essential to life and technology as we know it. Let's look at two powerful examples that make quantum tunneling very real. First, look up at the sun. The warmth of the sunshine on your face and the light that makes life possible all trace back to quantum tunneling. Deep in the sun's core, the temperature and pressure are enormous. Yet by classical physics, they still shouldn't be enough to make the sun shine. Here's why. To fuse into helium, protons, the nuclei of hydrogen atoms, must collide and stick together, but they are positively charged and fiercely repel each other, like two magnets with the same pole. The energy wall, called the Coulomb barrier, between two protons is extremely high. At the sun's core temperature, protons just don't have enough oomph to climb that barrier on their own. If we relied only on classical physics, the sun's nuclear fusion furnace wouldn't ignite. The sun wouldn't shine as it does now. Enter quantum tunneling. Even though any given proton pair usually can't overcome the barrier, there's a tiny chance they can tunnel through it. Once in a rare while, two protons find themselves suddenly together on the other side of that energy barrier, close enough to fuse. The probability is incredibly low for any given pair, but the sun has an astronomically large number of protons bumping around. Eventually, some fuse, releasing the energy that powers the sun's light. Quantum tunneling is literally the reason the stars shine. It allows nuclear fusion to happen in the sun's core, even though the conditions seem insufficient by classical rules. In fact, the sun's core is millions of degrees cooler than it would need to be without tunneling. Yet, fusion proceeds because quantum mechanics gives nature a little shortcut. So next time you see sunlight, remember, a quantum ghost dance of tunneling protons is helping light up our day. Now, from the vastness of the sun, let's come down to something you might find in a lab. The Scanning Tunneling Microscope, or STM. This device lets us see individual atoms by exploiting quantum tunneling. How does it work? Imagine a needle so sharp that its tip ends in just a single atom. This tiny tip hovers extremely close to a surface we want to image, but it doesn't quite touch. There's a tiny gap, perhaps only a billionth of a meter wide, a few nanometers or less. In classical terms, that gap is like an insulating barrier. Electricity shouldn't flow across empty space. But when the tip is that close, quantum tunneling takes over. Electrons from the tip can actually tunnel through the gap into the surface, or vice versa. This creates a very small tunneling current flowing across the gap, even though there's no direct contact. Here's the amazing part. This tunneling current is extremely sensitive to the width of the gap. If the tip moves just a tiny bit farther from the surface, the current drops off dramatically, essentially exponentially. If the tip moves closer, the current rises. By carefully scanning the tip across the surface and adjusting its height to keep the tunneling current constant, an STM maps out the surface atom by atom. It's like using the tunneling electrons as feeling fingers to trace the contours of the atomic landscape. Thanks to quantum tunneling, the STM can create images of individual atoms on a surface, revealing details as small as fractions of a nanometer. We can literally see atoms because of tunneling. And not only see STMs, can even move atoms around using tunneling current to push atoms, enabling scientists to arrange atoms into tiny structures. This technology earned its inventors a Nobel Prize and opened up the nano world, all relying on particles traversing a classically forbidden gap. Quantum tunneling shows up in other ways too. Radioactivity is another example. In some radioactive atoms, an alpha particle, 2 protons and 2 neutrons bound together, is trapped in the nucleus by the nuclear force. It's in a potential well with a high energy wall holding it in. Classically, it should stay there forever, but eventually the alpha can tunnel out, causing the atom to decay and emit radiation. Without tunneling, many types of radioactive decay wouldn't happen at the rates we observe. And in modern electronics, as we make components ridiculously small, tunneling can cause leaks of current through transistors. Engineers have to design around quantum tunneling or even take advantage of it. For instance, the tunnel diode and flash memory devices use tunneling to function. Even the emerging field of quantum computing harnesses tunneling in devices called Josephson junctions. It's amazing what once seemed like a quantum oddity is now a tool we use in laboratories and technology. Through these examples, from the heart of a star to the cutting edge of microscopy, one thing is clear. Quantum tunneling is not just an abstract theory, it's a fundamental aspect of how our universe works. It's a reminder that the world of the very small plays by its own rules, and those rules can be wonderfully counterintuitive. A particle vanishing here and reappearing over there. It sounds like a magic trick, but it's real physics, proven and even put to work in inventions. Quantum tunneling teaches us a beautiful lesson. Even when faced with a barrier that seems impassable, nature finds a way through. What seems impossible can indeed happen, given a chance. No matter how small that chance is, it's as if the universe whispers, never say never. If particles can tunnel through solid walls, maybe we too can find paths through the obstacles we encounter in life and knowledge. Every great scientific discovery is a kind of tunneling through the barriers of the unknown. So, let's carry that inspiration forward. The next time you hear about quantum physics and its strange phenomena, remember how quantum tunneling allows particles to achieve the impossible. In the spirit of science and curiosity, let's keep pushing boundaries and exploring new frontiers. Let's tunnel through every boundary of knowledge together.